Hello, good morning student. How are you? I hope you all are very fine, healthy and very happy at home. So what did we learn yesterday? We learned yesterday some of the application of the strength of acid on the basis of resonating structure. Nitrophenols are more acidic than the simple phenol. Again, there are the three isomeric phenol, nitrophenol we have seen. So, and then why para-nitrophenol is slightly more acidic than the orthonitrophenol due to the intramolecular hydrogen bonding that we have seen. Now let us see here, if the number of nitro group goes on increasing, let us see the here application number 5 maybe, that is a 2,4,6 trinitrophenol is more acidic than 2,6-dinitrophenol. Explain, right? Now what is our first job to do, our first things to do? Draw the structure of this organic compound. Look at here the structure of this. So this is the structure of phenol. We know that one of the hydrogen atom get replaced by the phenol, and then look at the numbering system. You can give number from counterclockwise or clockwise manner. So let us see 1, 2, 3, 4, 5 and 6. At 2 position, try. Nitro means which group you have to attach? You have to attach NO2 group. At 2 position, then at 4 position, and at this one at 6 position, and this is the structure of 2,4,6 trinitrophenol. So this is the structure of 2,4,6 trinitrophenol, and this one in short it is known as a picric acid. Common name of this is a picric acid. It is as strong as acetic acid, and it has a pK value is, I think pK value is equal to 0.65 or something. That is I think 1.26 roughly, not exactly, remember only as a 1.26. So this is the structure of picric acid. And why? And if you look at as a last one, the structure of 2,4,6 dinitrophenol. So that is the structure. It is very simple one again. Here OH is there at 2 position, nitro group. If you count 1, 2, 3, 4, 5 and 6, at 6 position, that is a nitro group over there, and therefore this is a structure of 2,6 trinitrophenol. So this is a structure of trinitrophenol, and if you see the pK value is found to be 4.1 something is there. So that is roughly. On the basis of their pK value, you can clearly understood that, or you can clearly say that those organic compound having lower pK value, they are the more acidic in nature, and therefore by comparing their pK value, we can easily say that this one is a strong, because there are 3 nitro groups are there, and as we know that nitro group exerts or shows minus I inductive effect as well as minus R inductive effect, both are increasing. The magnitude of that minus I inductive effect as well as minus R inductive effect is greater in this case, but here is a lower, and therefore this one is a stronger acid acidic in nature than this one. So that is the explanation. Now let us move on to the next one. Now we are going to learn about the resonating structure, the application on the basis of the bases. Now let us look at as some of the aromatic bases over there. Let us see here. First application on the basis of bases. So first application here, what is the aniline is a weaker base than the cyclohexylamine. Remember here, aniline is weaker base than cyclohexylamine. Aniline is a weaker base than cyclohexylamine. Explain. So how will you explain this? Aniline is a weaker base than the cyclohexylamine. Remember here again, aniline is a weaker base than the cyclohexylamine. What is our first things to do? First draw the structure of the organic. And we know that the structure of aniline is this one. The structure of aniline, this one. One of the hydrogen atom get replaced by the NH2 group, and it is an aromatic compound. Why aromatic? Because there is a cyclic compound, planar and alternative carbon-carbon double bond, fully conjugated is there, and therefore this is a structure of aniline. And aniline, I think, having as a pK value is, I think, 9.9 something. pK value, pKa is equal to 9.9, right? Now, why this one is a weaker one? If you draw the resonating structure here, this lone pair present on that nitrogen atom, they involve in the delocalization, so that you are going to get the structure this one. What are the changes I made here? Double bond NH2. Now look at on that nitrogen atom, again there are the 4 bonds are there, and therefore I am putting positive charge on the nitrogen atom, and at this corner point there will be a negative charge. Look at this carbon atom and this carbon atom, we not made any changes over there, so they remains as it is. So draw this one. Now again resonating structure, this negative charge forming the double bond between these two carbon atom, and this double bond concentrate the electron density at this corner point, and you are going to get the further structure, double bond over there, negative charge, this double bond here, then this one NH2 positive charge over there, and what do you get? Next one, this negative charge forming as a double bond over there, and this carbon-carbon double bond concentrate the electron density at this corner point, and you are going to get as the next structure, double bond, negative charge over there, this double bond and this double bond they are as it is NH2 positive charge. Then next structure we can draw this negative charge forming as a double bond over here, and this double bond concentrate the electron density, and you will get the further structure. What are the changes I made? Double bond and then NH2, this lone pair on it, this double bond and this double bond they are as it is. If you number these different structures, we got here one structure number second, this will be the structure number third one, this one is a fourth one, this one is a fifth one. And as I already told you that the number of resonating structure goes on increasing, the stability of that compound goes on increasing. Now this lone pair, when they start as a delocalization via unsaturated pi bond and coming on its original position, they take a longer time. And but in case of what will be the structure of next analogous? Cyclohexylamine is analogous of that aniline. Aniline is aromatic compound, but cyclohexylamine is a aliphatic compound because there will be a no carbon-carbon double bond. That's why it is a aliphatic compound. Now look at another thing you remember here. If the NH2 group attached to this carbon atom, that shows sp2 hybridization, and sp2 hybridization exerts minus I inductive effect, and here this carbon atom, the NH2 attached to this carbon atom, this shows sp3 hybridization, and that exerts plus I inductive effect. And as we know that plus I inductive effect increases the basicity, whereas minus I inductive effect decreases the basicity, and therefore this H plus, the lone pair which is present on that nitrogen atom, readily available for donation, it will pick up the proton from here, and you are going to get this one, and the conjugate acid form here, the conjugate acid form here, that conjugate acid is well stabilized due to the plus R inductive effect, and therefore aniline is a weaker base than the cyclohexylamine. So this is a first application of this thing. Okay, now let us move on to the next one. Let us see second application of bases is this one. Let us see here second application. Amides are neutral in nature even though they contains NH2 group. Amides are neutral in nature, even though they contains NH2 group. They contains NH2 group. Explain. How will you explain this? Now remember here again, amides are neutral in nature even though they contain as a NH2 group. If you remember, as I already told you, that those organic compounds containing nitrogen atom are basic in nature. Why they are basic in nature? Because nitrogen atom containing lone pair, according to as a Lewis acid base theory, it is capable of donating as a lone pair to the H plus ion, and therefore they are the basic in nature. And if you remember here, what will be the structure of amides? Primary amide. Remember here, the structure of primary amide is RC double bond O NH2. This is the structure of amide. Now the lone pair which is present on the nitrogen atom, it is not available for donation. Remember here. Why? Because adjacent to this lone pair there is a carbonyl group, and carbonyl group is an electron withdrawing group. It is attracting lone pair towards itself rather than, therefore we are getting as a resonating structure, double bond over there, negative charge on that oxygen, R, then CO minus double bond, then NH2 positive charge, means that lone pair are involved in the or engaged in the delocalization. It is not available for donation, and therefore amides, even though containing as a NH2 group, amides NH2 group, they are neutral in nature. So that is the reason why they are neutral in nature. Now let us look at as a next one. Next structure, that third application we are going to learn here. Third application, which is that third application. Let us see here. Third one, thalamides are acidic in nature. Thalamides is acidic in nature. Thalamide is acidic in nature. Explain. And I hope only few of you might be knowing the structure of thalamide, and most of you need not be knowing the structure of thalamide. So remember the structure of thalamide. So you might be knowing as a structure of phthalic acid, benzene ring, adjacent carboxylic groups are there. When it is treated with at a high temperature, maybe as a 200 degrees centigrade, or in presence of the Al2O3 alumina or concentrated H2SO4, these are the dehydrating reagent. They remove the water from that, and we are getting as a resulting compound is a phthalic anhydride. And that phthalic anhydride, when treated with ammonia, resulting compound is formed, that is known as a phthalamide, right? So don't think about that one. But here phthalamide, let us see the structure of phthalamide is this one. This is a structure of C double bond O, then C double bond O, here N and then H. This is a structure of phthalamide. This is a structure of phthalamide. This is a structure of phthalamide. When base is used here, base means OH minus, what it will do? It will abstract the acidic proton and form as a negative charge on that nitrogen atom, so that you are going to get here this one, then C double bond O, then C double bond O, N, then minus charge over there. This is a conjugate base form, right? This is a conjugate base. And when that conjugate base is well stabilized here, this conjugate base is well stabilized due to the resonance. This negative charge goes there on that oxygen atom, and you are going to get the product over here, this one, then CO minus over there, then nitrogen double bond, then C double bond O this way. Or you can draw the another structure, this coming return, forming as a double bond between this carbon atom and oxygen atom, and this double bond again concentrating the electron density on that nitrogen atom, and you will be getting the another structure here, this one, C double bond O, then N minus charge over there, then C double bond O, this one, and again you can draw the similar structure, this negative charge forming the double bond between this nitrogen and carbon atom, and at the same time this electron, this oxygen atom carries the negative charge, so that you are going to get the structure, this one, then C double bond O, then N double bond C, then O minus. This is a structure. In this way, this conjugate base is well stabilized due to the resonance. When stabilized due to resonance, and therefore phthalamide is acidic in nature. That is a thing over here. Now the last application remaining here, let us see that one also. Guanidine is the strongest base. 100% student, I know you don't know the structure what I just now altered one. What is that? Guanidine is a fourth application. Fourth one, guanidine is a guanidine is the strongest base explain, right? And guanidine, I know that most of you not knowing the structure of guanidine. What will be the structure of guanidine? Let us look at here. The structure of guanidine is this one, then NH2, then here double bond NH, and then H2N. This is the structure of guanidine. This is a structure of guanidine. This is a structure of guanidine, and as we know that there are the nitrogen atom, and therefore it is a basic in nature. And when it will pick up the proton, lone pair which is present on nitrogen atom, it will pick up the proton like this, and you are going to get here this one NH2 group over there, then double bond NH2, one H from here and one is there. So look at here H2N. What will be the charge on that nitrogen atom? I am putting positive charge because there are the 4 bonds, 2 with hydrogen and 2 with double bond. Therefore, and this conjugate acid formed, this conjugate acid is well stabilized due to the resonance. This is nothing but as a conjugate acid, and this conjugate acid is well stabilized due to the resonance. Look at here lone pair. This lone pair coming here, then neutralizing this positive charge, you are going to get here double bond H2N, then here NH2, and here this remains NH2, lone pair which is present on that nitrogen atom. Now let us look at here, positive charge comes on that nitrogen atom because there are the 4 bond, 2 with hydrogen and 2 with this double bond. Now this lone pair coming here and neutralizing this positive charge, so that you are going to get here double bond NH2, then this H2N and then NH2. So here positive charge on it. So in this way ETC you can write, and therefore this guanidine, this is the structure of guanidine, this is a conjugate base formed and after the donation of that lone pair, and whatever conjugate base is formed, that is well stabilized due to the resonance. This one is a well stabilized due to resonance, and that's why guanidine is a strongest base. So I think with this we have completed all the application, whatever applications are there that determining the acidity as well as basicity with the suitable example I have explained.